Hello and welcome to Calculus Tutorial. We are taking a look at the very beginning of the course today, the definition of the derivative. It's nice and ironic considering this is the very last video for first semester, but we've come full circle. And so we are again going to take a look at the derivative, which is the slope at one point. But there's a problem if you take a look at the tangent line at one point and you try to do the slope. So let's take a look at that. There's a problem here. What actually happens when you try to find the slope at one point? So we've got our slope between 2 points here. What happens when you try to take this slope between 2 points and shrink it down to only 1 point? So if I make delta x here all the way down to 0, we have a big problem. The slope, the tangent line, goes away. It is undefined because if you remember, slope, which is m equals delta x, what am I saying, delta x? Delta y over delta x. If I make delta x shrink down to 0, we are dividing by 0. And the fact that you get 0 at the bottom is why we've been studying limits for the past couple of weeks. That is how we're going to take care of this 0 in the denominator, is by looking at limits. And so to do that, we have our first point down here, some x value, and then f at x is our y value. X is the input. But then we have another point up here that's a little bit farther away. So we take that initial point x, but then we add delta x. That's this bit right here. And if that's the input, then our function output is, I'm simply going to put that inside x plus delta x. Okay, whatever's in the x value goes into the function to give us the y value. And so we have our 2 points, and we are going to find the slope between those 2 points. And then we have to somehow shrink delta x down to 0. We can't actually make it 0 because then that's undefined. Delta y over delta x. But we can approach 0, and so we can make that point closer, that delta x closer and closer to 0, but it can never actually get there because then our fraction is undefined. So that is going to be our definition of the derivative. Let's take a look at how that works algebraically. So let's get back to our PowerPoint here. There we go. Oops. All right. So we're now going to use limits to fix this tangent line problem and actually get a definition for the derivative. And so what I just written previously, we're going to take the limit as delta x approaches 0 of delta y, the change in y, over the change in x. There's two ways to think of the derivative: as a function or at the slope at one point. We've kind of stressed that multiple times through the course. The function definition and the point definition. And so we have two ways to write the derivative. So we're going to take the limit as delta x approaches 0. Now the bottom is going to be delta x. But on the top, we're going to subtract the y values. Delta y is just y minus y. So our 2y values, remember our point was x comma f at x, was the first point. And the second point was a little bit farther away, so we add delta x. That means that has to go into the input for your function, x plus delta x. So those are the 2 points. We are going to write that in the slope formula now. So we're going to take the y value and subtract the y value. So that is f at x plus delta x minus f at x. So there we have our definition of the derivative. Hopefully you can see on the top we have a y value minus a y value, and delta x is the definition of x minus x. So that is simply the limit of the slope formula. Now, without functions, we can still make a definition of the derivative that uses points instead. So that would give us the slope at one point, not the function. All right, so what would this look like? So this time our 2 points are going to be x, f at x again. But we're going to simplify the second point. It's just going to be a different x value, so we're going to call it c, and so our input would be f at c for our output. So those are our 2 points. And this time x is going to get closer and closer to c. So hopefully you can see then that the distance between these 2 points is also going to become 0. So the limit as x approaches c of f at x minus the other y value, which is f at c, divided by, now subtract the x's, x minus c. The difference between these two is when you do this limit, you will get a function. When you do this limit, you will get a number. And so that's the derivative at a point versus the derivative as a function. So that's kind of what we've been leading up to all semester, is the actual definition of the derivative, which is the slope at 1 point. All right, well now we're actually going to use that definition to do a few derivatives the hard way. So try not to groan too much. So let's do the limit as a function first. That's oftentimes the harder one. Let's see how that looks. And yes, you know the answer to this question super easily because you know the shortcuts, but now we're actually going to use the definition. So, using limits, we're going to find the derivative of f of x. So f prime of x is going to equal the limit as delta x approaches 0 of, and I'm going to write the definition first because it's new to us, and then we're going to put the numbers in. Alright, so there's the definition. So now when I plug these in, what will this look like? It's going to be a limit as x approaches 0. So we're going to do the easy stuff first. The bottom is going to be delta x. And then we are going to subtract f of x. Well, f of x is just 5x minus 7. So we are going to subtract 5x minus 7. The hard part is what goes first. So I have to take this, that is the input, which means all of that is going in for x. So we're going to have 5 times the input minus 7. What is the input? X plus delta x. And now it's all just algebra. Distribute, make sure your negative also distributes. So we will have the limit as x approaches 0. So we'll have 5x plus 5 delta x's minus 7 minus 5x plus 7 on the top, and on the bottom we still have delta x. So let's simplify and get rid of everything that doesn't need to be there. So a positive 5x and a negative 5x, cancel. A negative 7 and a positive 7, cancel. What is left over? On the top we have 5 delta x, and on the bottom we have delta x. Now we still cannot plug in, oops, I forgot my deltas there, didn't I? Put a delta there, please, and put a delta there, please, and put a delta there, please. I got ahead of myself. We still cannot plug in 0 for delta x because that gives us a 0 in the denominator. But thankfully, those delta x's cancel out, so the delta x doesn't even matter, and we are left with 5. And hopefully you can see that yes, the derivative of 5x minus 7 is in fact 5 because you know the shortcuts. But we just used the limit definition to show that that is indeed true. If you remember back at the beginning of the semester, I said if you'd like me to prove this rule to you, come on in on the weekend. That's what I would have shown you if any of us were actually there. Alright, next. That is what this looks like when you find the derivative as a function. What if we look at the derivative of a single point? The definition can still help us there. So use the limit definition to find g prime at 3. Alright, so g prime at 3 is going to equal the limit. I'm going to mostly just rewrite the rule here, but instead of a c, I know we're going towards 3. Of f of x minus f at, instead of c, I'm going to put 3 this time, over x minus 3. Alright, so that is just the slope formula, y minus y over x minus x. So what happens here? Well, f of x is simply this whole thing here. Although I guess I shouldn't have put f, should I? Sorry about that. That and that. Got my letters mixed up, didn't I? Should be a G. There we go. So we have g of x, which is 2x squared minus 5, minus g of 3. What is g of 3? Well, if I plug in 3 squared is 9, times 2 is 18. 18 minus 5 is 13. Divided by x minus 3. Alright, don't forget that in front we still have the limit as x approaches 3. I have to keep going because I cannot plug in 3 yet. So let's keep manipulating this. So we get the limit as x approaches 3. Simplify this on top, we get 2x squared minus 18, it looks like, divided by x minus 3. Still can't do that limit. Factor the top. Looks like we can pull out a 2. I'm going to do this kind of quickly here. X squared minus 9 is on top. This is definitely going to work. The top is a difference of squares, so we can factor that. That will be x plus 3 and x minus 3 over x minus 3. So now we actually can do the limit because that crosses out with that. So now I'm going to rewrite the limit here as x approaches 3 of simply 2 times x plus 3. Now we can plug in 3. 3 plus 3 is 6 times 2 is 12. Now, we can do that a whole lot easier. Oops. Trying to draw a dashed line here. Because we know derivative properties. We know g prime at x is equal to 4x. And so we know that g prime at 3 must equal 3 times 4, which is 12. So yes, our derivative properties make this much easier, but it's important to know that using limits and the actual definition, the math also works out. Okay? That is sort of the quote-unquote beginning of calculus technically, which we are now proving actually works. So we've got two definitions of the derivative, one for a function that uses delta x approaching 0, and one for the slope at one point where x approaches c.